But we're talking about hundreds of millions of times the mass of the sun. But it's a black hole, so it's small for that much mass.
Wow.
The sun goes around a black hole in the constellation Sagittarius at the center of the Milky Way galaxy.
Scientists have made a jaw-dropping discovery right at the heart of these enigmatic cosmic beasts. They've unearthed something mind-blowing and terrifying inside a black hole, challenging everything we thought we knew about these cosmic wonders. Buckle up, because we're about to unveil the astonishing secrets lurking within a black hole's mysterious core. Are you curious to know more? Let's dive in. Black holes are a fascinating phenomenon. You see, according to a brilliant scientist named Albert Einstein and his theory of general relativity,
the surface gravity is so high that you cannot escape it, even at the speed of light. You are forever trapped.
Gravity is not a force like magnetism or pushing and pulling. Instead, it's a result of how space and time are curved or bent by objects with mass and energy. Imagine you have a massive object, like a star, in space. It has an enormous amount of mass and energy, and this causes a deep dent or curvature in the fabric of space and time around it. This curved space and time is what we call a gravitational field. The more massive and energetic the object is, the stronger its gravitational field and the deeper the dent it creates. Now, keeping that theory in mind, let's talk about black holes. They are some of the most extreme objects in the universe, with unimaginable amounts of mass and energy packed into a tiny space. They have so much mass that their gravitational field becomes incredibly intense. This intense gravity creates a super deep and very strong dent in the fabric of space and time. Here's where things get really crazy. The gravitational pull near a black hole is so incredibly strong that it forms what we call an event horizon.
That the event horizon is not some wall, it's just space moves smoothly through and across the event horizon.
This is like an invisible boundary or point of no return. Once something, like an unlucky spaceship or even light, crosses this boundary, it can never escape the black hole's grasp. It's as if the black hole has an invisible force field that holds everything inside, including light, which is usually the fastest thing in the universe. Just to emphasize how extraordinary this is, imagine you're shining a flashlight. The light beams travel really fast, about 300,000 kilometers per second. But if you were somehow inside a black hole, the speed you would need to escape its clutches would be even faster than the speed of light. That's impossible according to our current understanding of physics. So, any light that enters a black hole becomes trapped forever, unable to break free.
Light into the black hole. Light coming from farther away gets bent around it.
So, when we talk about a black hole, we can't forget about its mysterious boundary called the event horizon. It's like a point of no return for anything brave or unlucky enough to venture across it. Once something crosses that boundary and falls into a black hole, it's a one-way trip with no turning back. The event horizon isn't something you can physically touch or see. It's more of a mathematical concept that tells us where we can no longer observe what's happening. You might be wondering, how big is this event horizon? Well, it all depends on the mass of the black hole itself. The more mass a black hole has, the larger its event horizon will be. Scientists came up with a formula to calculate the radius of the event horizon, and they named it the Schwarzschild radius, after an astronomer named Carl Schwarzschild, who figured it out back in 1916. To find the Schwarzschild radius, you divide the mass of the black hole by a constant that involves the gravitational constant and the speed of light. For example, if we had a black hole with a mass 10 times greater than that of our sun, its event horizon would have a radius of about 30 kilometers. In the heart of a black hole is what is known as the singularity. All the mass and energy of the black hole, no matter how mind-bogglingly huge, is squished and compressed into an infinitely tiny and dense point at the center. We call this point the singularity. It's like a cosmic heavyweight, packing an incredible punch of gravity and curvature. In fact, the singularity has infinite curvature and infinite gravity, which is pretty fascinating. But here's the catch. Our understanding of physics starts to crumble when we try to make sense of what happens at the singularity. We simply don't know what goes on there. It's as if the laws that govern our universe take a break or go on vacation, leaving us scratching our heads in wonder. Scientists are still exploring this enigmatic territory, hoping to uncover the secrets hidden within the heart of black holes. And how do black holes come into existence? You know, it all starts with the life cycle of a massive star. These stars are like cosmic powerhouses, fueled by incredible nuclear fusion reactions happening deep within their cores. Imagine these reactions as a fantastic cooking show.
A specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
Where hydrogen atoms combine to form helium atoms, releasing an enormous amount of energy in the process. Now, as long as the star has enough hydrogen fuel to keep the fusion going, it remains stable. But stars are greedy, and they want to keep the fusion party going. When they run out of hydrogen in their core, they get a little creative. They start fusing heavier elements like helium, carbon, and oxygen. Each fusion reaction with heavier elements produces less energy than the previous one. To compensate for this, the star has to work harder and burn faster, turning up the heat to maintain its delicate balance. And sadly, every star's journey must come to an end. The star reaches a critical point where it can no longer fuse any more elements. At this moment, something extraordinary happens. The star's core collapses under its own tremendous weight, like a magnificent implosion. And there you have it, a black hole is born. When the core collapses, it forms the heart of the black hole called the singularity, which we talked about earlier. This singularity holds all the star's mass and energy in an incredibly tiny space, creating an intense gravitational pull that not even light can escape. It's like a cosmic vacuum cleaner, sucking everything into its gravitational embrace. And when a star is approaching the end of its life, what happens next depends on its size, or in other words, its mass. Let's break it down into 3 stellar weight categories. First up, we have stars that are smaller than about 3 times the mass of our Sun. These stars are in for a transformation. Instead of going out with a bang, they become something called a white dwarf. It's like the star decides to retire gracefully. Inside, it's a dense ball made up of carbon and oxygen atoms, which continue to emit light as residual heat. Now, if the star happens to weigh between about 3 and 20 times the mass of the Sun, get ready for an explosive spectacle. These stars go out with a massive supernova bang. The core of this star, amidst the chaos of the explosion, undergoes a dramatic collapse. It becomes a super dense ball known as a neutron star. Imagine squeezing up to 2 times the mass of our Sun into a tiny sphere with a radius of only about 10 kilometers. Now, if we're talking about a real heavyweight star, there are ones that weigh more than about 20 times the mass of the Sun. These stars also explode in a supernova, just like their slightly lighter counterparts. However, the core of these mammoth stars has a different destiny. It collapses under the weight of its own gravity, and it doesn't stop there. The gravity becomes so incredibly intense that the core shrinks down to 0 volume and infinite density, which again results in the birth of a black hole. Black holes have a couple of types. We have stellar mass black holes. These are the ones that form from massive stars nearing the end of their stellar journeys. They typically have masses ranging from a few times to several tens of times that of our dependable Sun. Stellar mass black holes are actually quite common in our galaxy and other galaxies out there in the vastness of space. Now, let's shift our gaze to the colossal supermassive black holes. These cosmic behemoths are the true giants of the black hole family. They boast masses that are millions or even billions of times greater than that of the Sun. Picture them as the masters reigning at the centers of most large galaxies, including our very own Milky Way. These mighty black holes are thought to have formed during the early stages of the universe, born from the collapse of massive clouds of gas and dust, or from the merger of smaller black holes. Their presence greatly influences the evolution of galaxies, shaping the formation of stars and planets that dance around them. Now we come across a rare breed known as intermediate mass black holes. These elusive creatures sit right between the stellar mass and supermassive varieties in terms of mass. They are like the middle children of the black hole family, somewhat mysterious and not commonly spotted. Their origin is still a bit of a puzzle, but scientists speculate that they may have formed from the collapse of incredibly massive stars during the early cosmic eras, or from the union of stellar mass black holes in dense and bustling star clusters. Lastly, we have the intriguing primordial black holes. These are the potential relics from the very beginnings of our universe, born shortly after the Big Bang itself. They emerged from fluctuations in the density of matter and energy during those cosmic early moments. Primordial black holes come in a wide range of sizes, from minuscule ones with masses just a fraction of a gram, to massive ones thousands of times heavier than our Sun. It's important to note that while they are a captivating idea, primordial black holes remain hypothetical and have yet to be directly observed. Black holes have another interesting aspect: their rotation. For instance, there are the Schwarzschild black holes. These are the simple and straightforward ones. They don't spin. Think of them as the calm and steady black holes of the bunch. They are described by the Schwarzschild solution, a mathematical description in Einstein's theory of general relativity. These black holes have a nice spherical event horizon, which is like a boundary that marks the point of no return, and a singular point at the center called the singularity. It's like a singular dot with an immense gravitational pull.
In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future.
Next, we encounter the Kerr black holes. These ones are all about that spin. Kerr black holes are described by the Kerr solution in general relativity. They have an oblate or slightly flattened event horizon and a singularity that takes the shape of a ring. The rotation of a Kerr black hole creates something called the ergosphere. This region around the black hole is like a cosmic whirlpool, where space and time get dragged along by the spinning black hole. Now let's meet the Kerr-Newman black holes. These are the rock stars of rotation, with a little extra something. They not only spin but also carry an electric charge. Kerr-Newman black holes are described by the Kerr-Newman solution in general relativity. They share many similarities with Kerr black holes, like their oblate event horizon and ring-like singularity. However, the electric charge adds a twist to their story. The event horizon and singularity get a bit distorted by the electric field. And scientists have discovered ultramassive black holes. You see, an ultramassive black hole is a truly extraordinary cosmic heavyweight. It tips the scales at more than a whopping 10 billion times the mass of our trusty Sun. We're talking about a black hole that's so massive its gravitational pull is unimaginably strong. Anything that ventures too close to it would be in for a wild ride. Now, how did we even discover these cosmic monsters?